Jake, you asked me why the wires repel. Why do they move apart? And I've come to the conclusion I can't tell you the answer to this all in one go. So what I'm going to do now is give you the short answer, and then we can I can go into perhaps afterwards on another talk give you a deeper answer. But what you can't see from the video is just exactly how the wires are set up. So first I'll just tell you that. Here's the no, it's terrible. Here's the polystyrene block. Okay. And in one end you've got a piece of wire stuck in with a hook, and another piece of wire stuck in with another hook. And on this end there's a piece of wire stuck in with a hook. And then hanging from this hook is a piece of copper wire that's looped over, and it goes all the way across here and there, out like that. And then this one has a similar thing. Alright. At this end they're on separate hooks, but at this end they're on the same hook. So that means that what we do is connect these two things to a battery, like that, and there's a current then flows. It would actually be, let's just get rid of that because that's a bit in the way. This would mean that there's, on this bottom one, there's electrons flowing in this direction, and on that one there's the electrons flow back. So the point is that the current is flowing in opposite directions in these two wires. Right, I'll look a bit more closely at that now. So essentially it's something a bit like this. Connected to a battery, like that, and this is the positive end of the battery. This thing sticking out is the positive end on batteries, and so the current is flowing around here. And it's normal in physics or engineering to give a current, an electric current, a label capital I. Sometimes, yeah, usually capital I. Not, and so, but in fact, what is actually happening is that electrons are flowing in the opposite direction. The electrons are flowing along here. I'll give that little sign there as an electron. Right. The reason this opposite direction thing is, it's the historical thing that when they first talked about currents in wires, they weren't aware that it was actually a flow of electrons which are negatively charged. So I want to look more closely now at this bit. Okay. Here's the wire at the top. This is a bit of the wire. That's not very good. That's what I meant to draw. like that. And this is a piece of copper wire, and in this copper wire there's copper atoms dotted around in a structure. Actually, they're not atoms, they're copper ions. They're ions because they are charged. They're positively charged because they've lost their electrons. Not all of them, I suppose, but some have lost their electrons, and these electrons can flow around. Right. Yeah, there's one there. I've drawn them sort of spaced up like this, but although the copper ions are distributed in a structure, the electrons are just flowing. They can be anywhere more or less, but they're, yeah. And I said that in the top wire the electrons are flowing in this direction. Right, so here we are. Whereas the copper atoms are fixed. Now, if we consider now an electron in the other wire, it's moving in this direction. So how does it see this arrangement? How does it feel about these things? Because there are equal numbers of ions, copper ions and electrons in the wire, the copper wire is neutrally charged. There's a net charge of 0. So there's no attraction because of the wire, or repulsion because of the wire, and this electron in the other wire. But special relativity says that lengths contract. I just want to draw this a bit closer because I want to use that space. Lengths contract. What that means is that if there is a 1 meter rule coming past, and you have your own 1 meter rule, if you compare, as this passes, if you compare the lengths of these two, it will look as though you will measure this one to be shorter. Strange, isn't it? And this is because this stems from the fact that a fact in special relativity, and that fact is that the speed of light you can't see that because of that lamp, is always three times 10 to the 8 meters per second. Three times 10 to the 8 meters per second. and that is actually it's a tiny bit less than 3, 2.99 something. But it's this, whenever light speed is measured, its speed of light is measured, it's always this speed, no matter whether you are travelling at high speed towards the source, maybe a star, or at very high speed away from it. You always measure this speed, and because of that, there's a whole load of things that this affects in although you don't see them because the speed of light is so big. There are things like mass, energy, all sorts of things in physics which are altered by the fact that this is constant, and this gives us the special relativity. Special relativity is to do with high speeds, whereas in normal life we don't see any of this happening. So anyway, how does this affect this arrangement? As this electron is travelling in this direction, it sees the wire going in that direction. That's its perspective, that's its viewpoint, the wire travelling in that direction. But it sees the electrons travelling twice as fast. So although there is wait a minute, and this means that because of this length contraction between the electrons, the spacing between the electrons seems to this one to be shorter than the spacing between the copper ions. So there seems to be a compaction of the negative charges. And so, because it's under motion, this electron feels, because of this compaction, it feels that this wire is charged, negatively charged. And so this negative charge or relative negative charge, because of this relative of the wire, and the negative electron, which is a member of the other wire. There's a whole load of other electrons in the other wire, but for each one this is happening, and so they feel a repulsion. Now, as I said, that the effect of this is so huge, this number, that actually these electrons are only travelling through the wire, typically a millimetre per second or something like that. So if there's a current of say 10 amps in a wire that's a millimetre across, it's something like, these travel at something like a millimetre per second, that's all. And so the speed of these is very low. It's not a very high speed. So the contraction, this compaction, is tiny, tiny, tiny. However, the charge, the electric force, which is what these push, is something like 10 to the 24, that's a big number, times the force of gravity. And so because of this tiny compaction, there is nevertheless a significant force between the two, the repulsion. And if you do say if you look at the situation, if the wires actually were sending and the current in both wires the same direction, you get the same effect, except you get the same kind of thing, except that there's an attraction between the wires. This is why this actually happens. The explanation classically is that there is a magnetic field around the wires and that the magnetic fields repel. But more fundamental is this, and which gives rise to this contraction. And actually there's not a magnetic field. What there is a charge repelling each other. Charges repelling. Of course, what this doesn't explain is why the charges repel. We don't know. Okay. Thank you.